Okay, I think I'm back up and running again. So we left off just briefly talking about the difference between selectively permeable, impermeable, or freely permeable structures across the cell membrane. And so things that will affect the permeability are things like size and charge, the shape, as well as the solubility. Things that are lipid soluble tend to not um, go through that cell membrane because of that lipid that phospholipid bilayer, that kind of polarity that exists with that phospholipid bilayer. So it's important to understand how that structure will really affect the permeability at hand. And speaking of permeability, then we get into the different types of transport, something like simple diffusion, just things going in and out very passively. Solutes will move down their concentration gradient until equilibrium, right? Everything moves and shifts until an equilibrium or a balance is reached. So things that affect diffusion, things like the distance or the length of space that that particle has to travel, the molecular size, temperature, right? If it's warmer, it's going to dissolve or spread much quicker than when it's cooler. The gradient size, if it's just the difference between a 51% and a 50%, or if it's a 3% and a 90% across the membrane, that's going to happen a much quicker, much more rapid diffusion rate than something that's very close to equilibrium state. Electrical forces can play a role as well. Something like filtration is a different process. Filtration is using a pressure gradient, which is different than an osmotic gradient, but you can think of it as the same concept. It's high to low, but instead of lots and lots of molecules in one space, it's more about pressure, which is kind of related to mass and volume in a way. So that's going to form this thing called net filtration pressure. You have osmotic pressure and hydrostatic pressure, which will balance out and create this thing called net filtration pressure. One's pushing something out, one's pulling something back in, and they are opposing forces, and they play a huge role in our in our digestive system, in our circulatory system, in our respiratory system. So you're going to visit filtration many times this semester as we look at how things pass through, like capillaries, for instance, like in this picture here. I don't know, I guess you can see my mouse. In this capillary bed, you have the filtration pressure pushing things out on the arterial side of the capillary, and then reabsorption happening on the venial side of the capillary. And we'll get into all of that once we get into, I think it's chapter 21. A couple more things to talk about. Tonicity, right? Isotonic, hypertonic, hypotonic. You should understand those terms, how they relate to one another, how they relate to solutions, how they relate to cells. Super important to understand that, and the effects on the body, not just, a cell sitting in a petri dish somewhere. I think we're finishing up things here. The idea of carrier-mediated transport and facilitated diffusion, actually using some type of pump or carrier to move things across the membrane. Very important to understand how those work differently than something like simple diffusion or osmosis. There's also co-transport and counter-transport, remember? That's when two things are either coming through together or they're moving in opposite directions. The sodium-potassium pump is an example of moving in opposite directions, right? Sodium goes one way, potassium goes the other way. That would be a counter-transporter. Co-transporter would be like glucose and sodium. They always come in or go out together. They like to travel hand in hand, so to speak. There's also active transport. Active transport is a type of carrier-mediated transport. It's using a pump, but in this case, it's not just using a pump that's passively, or rather a protein that's passively allowing things to flow through it. In this case, active transport is actually using energy, actually using ATP to get things across the membrane. The sodium-potassium pump would be the big example here. Other ion pumps can do that as well. So here's an image of the sodium-potassium pump, where you have the outside of the cell, which has a very high concentration of sodium. The inside of the cell, just figuring this out. Sorry about that. Don't know what's going on there. The inside of the cell, which has a very high concentration of potassium, and that sodium-potassium pump is continuing to pump potassium into that cell, even though it already has a lot of potassium there. it continues to get more because this pump is actively pushing it in. Something important to understand. Secondary active transport is when you have other things going on that are going to affect the rate of transport, something like glucose and sodium, as I mentioned, affecting how the sodium concentration is going to level out. There's also bulk transport like endocytosis and exocytosis. Endocytosis is bringing things into the cell. That could be like pinocytosis or phagocytosis, and exocytosis pushing stuff out of the cell, getting rid of it, being released into the world. Endocytosis can be receptor mediated, meaning there's special areas on the outside of the cell that are therefore receiving incoming vesicles and kind of taking them in, taking them to the Golgi and getting them sorted and processed. And pinocytosis and phagocytosis. Pino is the drinking and phago is the eating. Eating, it's not really eating, but it's kind of like that. Here's just a little image so you can see the endocytosis side and then the exocytosis side. This bacteria comes in, it's engulfed, that would be like phagocytosis, and then these little lysosomes coming off of the Golgi engulf that bacteria, gobble it up, and then spit it out. That's the exocytosis. And it's basically the reverse of exocytosis, as I said. This chart is just going through all of the different types of movement, ways that molecules get across the cell membrane. And, last couple of concepts. Transmembrane potential, super important. This has the idea kind of linked to this ion concentration issue, right? If you have lots of potassium, which is positively charged, and sodium, which is positively charged, well, then the cell's going to have a charge, right? And that's the whole idea of this transmembrane potential. Super important to understand. And our resting cells have an unequal transmembrane potential, or RMP, resting membrane potential. The resting values are going to range depending on the type of cell, negative 10 millivolts to negative 100 millivolts. Again, depending on which type of cell we're talking about, how excitable that cell is. Something like a skin cell isn't that excitable. They don't really do anything. Something like a muscle cell or a nerve cell, those are highly active, so they're going to have a much lower resting membrane potential. And ultimately, this transmembrane potential is determined by that sodium-potassium balance and that distribution across the membrane. So the sodium-potassium pump plays a very important role here. The cell's interior has a greater concentration of potassium, the exterior has the sodium, and that sodium-potassium pump continues to keep that balance. And there are passive and gated channels that work to allow the free flow of potassium back into the cell or the free flow of sodium out of the cell. And those channels can be activated and deactivated at different times, again, depending on the type of cell and exactly what that cell's trying to accomplish. More potassium diffuses out, then more sodium diffuses in. It's going to be a one for one. Ultimately, that loss of the positive charge creates this negatively charged cell, and we say that cell is polarized. And that polarization can then cause a kind of a chain reaction that we'll look at later. If too much potassium is left in the cell, it will become too negative, and we call that hyperpolarization. Then if sodium were allowed to actually accumulate inside of the cell, it would become less and less negative, or positive, right? And that cell is then said to be depolarized. Bringing that sodium into the cell changes the tonicity, it changes that transmembrane potential, it depolarizes the cell, it makes the cell highly active, kind of wakes the cell up, and gets that cell ready to do whatever it is it's supposed to do. If it's a muscle cell, that influx of sodium is going to allow that muscle cell to get ready to contract. So influx of sodium is generally, getting that cell up and ready. So that sodium-potassium pump reestablishes that osmotic balance and that transmembrane balance. I just have about 20 seconds left here in my little video clip. This is just that graph. You should be familiar with this, right, from last semester. The whole depolarization, repolarization chart and graph. It's important to understand how the diffusion gradient works, how those different channels play a role. And, neurons. Neurons need a constant supply of glucose and oxygen. That's my video.